Time for some B1M. Specifically, is America about to win the nuclear fusion race? Now, what race is that? To say we're less than 20 years away? For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge.
There are complex building sites, and then there are these. For decades, scientists and engineers have been trying to construct giant machines that recreate what happens inside the sun.
Yes, and we don't have that strong solar gravity to help us out.
Say it with me, nuclear fusion. It's where, instead of splitting atoms to generate power, like with nuclear fission, they're forced together at extreme temperatures. If successful, these systems could bring about a virtually limitless source of energy. But
good for the high-level description, but it isn't limitless. Deuterium is abundant, but tritium is not. It must be bred within the reactor using lithium blankets. Without breeding, tritium supply is going to run out in a couple of decades or so. Even faster if fusion actually gets adopted for large-scale energy production. So by that same logic, nuclear fission is unlimited if you're automatically taking credit for your supply chain. Neither are. But I can understand why a lot of people throw that out there, and that's so people would continue to invest in this stuff, is to say it's virtually limited. Which, with proper supply chain and planning, can be sustainable, but we're not there yet. And even if we were, there's a big difference between sustainable and limitless.
unsurprisingly, it's proving to be immensely difficult, with even huge multinational collaborations struggling to make it work.
Ether.
But now a new player has entered the race. It's a small, privately funded US startup that's making rapid progress. And not only is it catching up to its much bigger competitors, it looks like it might just win a race to master a technology that has, at times, seemed impossible. So, if you're not a regular viewer of the B1M, then right about now you're probably thinking, what on earth is nuclear fusion?
Alright, let's see how they explain it.
If you want a full rundown, it's worth going to check out the video we did back in 2024 when I travelled inside the world's largest nuclear fusion reactor that's currently under construction down in the south of France.
If you haven't seen my reaction to that one, please be sure to check it out. I'll pin it in a comment down below.
If you're off to do that, great, but keep this tab open, come back and finish this video, we'd really appreciate it. If you don't want to do that, if you think it's all a bit technical, then don't worry, because we've put together a simple summary of nuclear fusion. Basically, nuclear fusion is where you take a whole bunch of hydrogen atoms, heat them up a lot, we're talking over 100 million degrees Celsius, and bring them to the point where they form a plasma. This causes them to fuse together and create helium and neutrons, generating huge amounts of energy.
Not a bad quick explanation. You need ridiculous high temperature, ridiculous high pressure, and confinement time so they can do it. Keep in mind that 100 million is actually relatively cold compared to the sun, but the sun has all that gravity to compensate for that. We don't have anything like that on Earth, which is why we have to go hot. The sun's only about 15 million degrees. And they are correct in using deuterium tritium as the fuel choice in this case. Both of these are the less common isotopes of hydrogen. I say less common. Deuterium is still pretty abundant. It's actually used as a coolant in certain types of fission reactors because it's a good moderator of neutrons that slows down neutrons so they can cause other fissions. Even better than light water or just basic H2O, D2O, which is still chemically the same thing as water, only heavier. Slows down neutrons even more so it can use natural uranium in can-do reactors and other similar designs that use heavy water. Tritium's rarer though.
It all happens in a special donut-shaped vacuum chamber known as a tokamak. Inside, a series of magnetic fields confine the plasma and suspend it within a space known as the torus. That way, it can be kept apart from anything solid.
Again, not a bad explanation for a layperson.
The fuel we have inside the tokamak is a mix of deuterium and tritium, which are both types of hydrogen. You need very, very small amounts of fusion fuel. So like over the course of a year, a 400 megawatt net electric arc power plant will use roughly 100 kilograms of fuel.
So 400 megawatts electric is pretty small compared to most fission reactors that are on the order of a gigawatt or 1,000 megawatts electric. And while 100 kilograms doesn't sound like much, because it's not, compared to the nuclear power plant that I worked at that had 193 fuel assemblies that each weighed about a ton. Now, that's not just the active ingredient, the uranium fuel itself, that's also the cladding as well as the support structures to house the fuel, but that's still way more mass. And fusion is a fair bit more abundant in terms of energy released per unit mass than fission, on the order of 3 to 4 times. But 100 kilograms is still kind of a lot, mainly because you're handling several grams of tritium. It has a tendency to leak, it diffuses, I mean, it's still hydrogen, and it contaminates everything. It's a bit like saying a nuclear submarine only needs a few kilograms or so of uranium every decade, and that's nice and easy, but there's still a complicated nuclear fuel cycle involved with highly enriched uranium in that case, that you need quite a lot of infrastructure in order to maintain that.
Now, the superconducting magnets that make all this possible have to be incredibly strong and able to withstand those crazy temperatures. And usually they have to be absolutely massive and made from complicated sounding materials like niobium tin, which are very hard to come by. But that's not necessarily the case anymore, as we'll discover.
Speaking of hard stuff to handle, though not as much as, say, the tritium itself, but yeah, quite a bit of materials processing and fabrication that has to go on there.
Bits. If you're still with us, then well done. When I visited ITER in the south of France, that's the
I actually thought that explanation was pretty good.
thermonuclear experimental reactor, it was an amazing experience. The place is absolutely epic, both in its scale and its ambition. But as I discovered when I was there, there's been a few setbacks and delays, because building a nuclear fusion machine is extremely difficult.
Doing anything on that scale, first of kind, really sensitive materials, that many different groups of contractors that have done things that they've never seen before. Oh yeah, the project management is a nightmare.
Another key thing to remember about ITER is that it's basically a huge experiment and won't provide electricity for people to actually use. Whereas this firm over in America is planning to construct a fully operational tokamak and is on the way to building a power plant that can bring nuclear fusion power to the grid, something
that's ultimately what we want with fusion, right?
Which has never been done. Commonwealth Fusion Systems is the name, and it's considerably smaller and younger than that huge organisation over in Europe, which was formed way back in the 1980s. CFS was only founded in 2018 by a team from the Plasma Science and Fusion Centre, which is part of the famous Massachusetts Institute of Technology, or MIT.
We are basically trying to build fusion power plants around the world and use that to make, firm, clean, abundant energy. We're about 7 years old as a company. We're about roughly 1,000 people now.
Nice.
So we've grown a bit in those years.
So how are they going to harness that power and get it to the grid? Well, there will be something surrounding all that plasma in the tokamak.
We're going to use the same thing we've used for the past 200 years.
It's called a blanket made from a type of molten salt. That's going to heat up and generate steam, with the rest of the system set up in a similar way to a nuclear fission plant.
Or a natural gas plant, or a coal plant. That whole part of it is been around long before nuclear fission has been around. Even those hyperbolic cooling towers that you see right there, that design predated nuclear fission reactors by quite a bit. It's interesting how old some of this technology is.
All the steam gets passed through a turbine, which then turns and generates electricity. As for where the plant's going to be constructed, it'll be happening...
Good old steam. Hey, if you're trying a very new concept, I can tell this one at least has enough clout to just stick with a similar secondary plant, the non-nuclear part of the plant that takes the steam, spins a turbine, condenses the steam, and sends it right back in as feed water. Unlike some of these other firms that claim they're going direct to grid without using a steam turbine, trying to throw in too many new things all at once. This at least shows some level of discipline with how much you innovate at once.
Right here on this plot of land in Virginia, just outside Richmond. It's time to focus on that nuclear fusion plant. Called ARC, it'll provide 400 megawatts of fusion-generated electricity straight to the state's power reserves.
I know I mentioned earlier about 400 megawatts being small compared to nuclear fission plants. As far as making the first one, though, that's actually a decent size. Some first-of-kind fission plants were less than 100 megawatts electric. Some even less than 100 megawatts thermal, which would figure out to about 30-something megawatts electric. So this is a decent size to start off with.
That's enough for around 150,000 homes, and the plan is to have it running by the early 2030s. Now, if you're a Marvel fan, that
All right, so now we're looking at 5-10 years away as opposed to 20.
name might sound familiar. The glowing thing that powers Iron Man's suit is called the arc reactor, and it was based on the idea of nuclear fusion.
Yeah, if that was the case, these guys would be getting nasty neutron dose.
Arc reactor was a stepping stone to something greater. Something so big that it was going to make the nuclear reactor look like a AAA battery.
Now,
I don't recall how that reactor is supposed to work, but it could be using some sort of sci-fi material far more abundant than fission or fusion, for that matter.
we don't know whether CFS's plant is a nod to this or just a coincidence, but either way, nuclear fusion machines are now
ARC's a
something
pretty common acronym, though.
you're not going to see just in the movies. This is happening for real. And just like Tony Stark, the company's teamed up with some powerful allies to complete its worthy mission.
Dominion Energy, the
Okay.
largest utility company in the state of Virginia, has signed up to provide expertise and
Yeah, they have quite a few fission reactors, so that's good. Collaborating with existing industry and not... That's great. That could also help them go the power route rather than the research route.
leasing rights for the site. They've been getting plenty of financial backing too. So far, the firm has received more than $2 billion in private funding, with Bill Gates as one of its investors, and it's taken in millions of dollars in grants. Another sign that CFS should be taken seriously came in the form of a new strategic partnership with Google. Signed in June 2025, it's a deal that saw the tech giant agree to purchase 200 megawatts, yes, half, of all the power generated from this first plant. Google has the option to buy power from future plants as well.
The opportunity to say you're one of the first customers from nuclear fusion, I'm sure that is also a big thing they want to push towards as a big name in tech.
And it's also upped its stake in CFS, although details of that haven't been released just yet.
So they're not short of money or big name partners, but surely you can't just go and piece together a nuclear fusion power plant, something that's eluded scientists for decades, without building some kind of prototype first.
Well, yes, which is why they've been doing exactly that. Before they build the Ark, they need to finish this, the Spark. Under construction in Devons, Massachusetts, which is about 50 miles northwest of Boston, it's a demo project that CFS is going to use to prove that commercial fusion is actually possible.
All right.
We have to build
Proof
the
of
tokamak itself,
concept.
but we also have to build a facility around it to support and operate the machine, and also to take the fusion heat out. We have a tokamak hall that has 4 wings around it, and I like to think that each of those buildings has something that either goes into the tokamak or comes out of the tokamak.
Firstly, there's the operations building, which is full of diagnostic equipment used to run the machine and monitor what's happening inside. Then you've got the radio frequency heating building, which houses all the electronics needed to cook the hydrogen fuel up to the right temperature. I say cook because it works in a similar way to a microwave oven, except it uses radio waves instead.
Sure. So it's a combination of radio frequency heating, neutral beam injection, and ohmic heating. So it gets kind of complicated there. This would be the equivalent, if this was a fission reactor, this would be like having 3 different startup heaters, 3 different ways to maintain neutron flux before achieving criticality or equilibrium during startup.
Now, I don't need to say this because you've made it this far into a nuclear fusion video. You're already a reasonably intelligent human being.
I wonder if he's had a lot of views drop off for things being too technical from his normal audience. I don't know. I actually think, as far as the high-level explanations, have gone pretty well.
But remember, this is for cooking plasma, not pizza. Don't try and cook a pizza in a tokamak, because you're going to
Now, you can get plasma in a microwave. Just put a couple of grapes in there.
end up with it very well done. And you'll have personally sabotaged mankind's shot at clean energy.
I mean, yeah, if you throw a pizza in there, that would be a pretty serious FME event or foreign material exclusion event. There's a whole program in fission plants designed to prevent FME type incidents. So yeah, don't do that.
Next up is the power building, and that's where all the electricity that goes into those magnets comes from.
Okay.
Finally, there's the utility building, which no, is not full of washing machines and cleaning supplies. The utility room is much cooler, quite literally. As well as being the place where the fusion heat is removed, it's home to all the cryogenics equipment for keeping the magnets cold, like seriously, seriously cold. We're talking lower than minus 400 degrees Fahrenheit.
This is the funny thing about fusion and why there's immense engineering challenges. You have something that's 100 million degrees Celsius, and then you have something that's minus 240 degrees Celsius that are not that far away from each other in the grand scheme of things. Certainly not impossible to do. I mean, obviously it's in the process of being done, but temperature gradients aren't that big. And compare that to a fission reactor where core exit thermocouple temperature, which is the highest temperature that you measure in Celsius, that's going to figure out to 400 degrees at most. Those are thermocouples from the reactor coolant system that's exiting the core. The actual fuel pins themselves, the center line, the hottest part, 2000. And as far as the coldest thing, well, that's going to be the tertiary cooling loop in the reservoir, which is going to be ambient, 10-15 degrees Celsius on a relatively cool day.
Going back to the tokamak, one thing that makes the Spark one different to others that have been built before is the approach being taken with those magnets. Although they might look similar to the ones used at ITER with the same D shape, they're actually made from something else. Developed by CFS, they use a new type of material called REBCO, which stands for Rare Earth Barium Copper Oxide.
Okay, this is the X factor here. That'll give you a much stronger magnetic field. Discovered
in the 1980s, but for a long time you could only make like tiny quantities in a lab somewhere. But in the last like maybe 10 years or so, a number of companies around the world have ramped up production of that considerably, so you can make industrially relevant quantities of it now.
Nice.
And our innovation was take that material and engineer a magnet out of it.
According to the company, these magnets are so strong they can be smaller than ones found on other tokamaks, which means the whole system can be scaled down as well. That's pretty obvious when you look at where they're building their prototype reactor. This place is big, but it's still dwarfed by the enormous ITER enclave. Yeah. The idea is to have Spark producing its first plasma as soon as
I mean, you can see the different size. You can see a guy can barely fit in there, whereas the other one whether it's ITER, you can walk standing up in there.
26.
Once that happens, the focus is then going to switch to reaching net positive state. That's where more energy is coming out of the nuclear fusion reaction than goes in to power it. And only once they've got to that point...
That's a pretty key break-even point.
Are they then going to go and build the main plant.
This is referred to as Q greater than 1. Keep in mind, for large-scale production, greater than 1 isn't enough. For it to be economical, you're probably going to want it to be greater than 20. And that would account for the magnets, the cryogenics, the power conversion, all the support systems you would have to run for it to be even remotely worthwhile.
There's also another reason why CFS appears to be in a bit of a hurry. This is not a one-horse race. It has competition from other groups who also believe they have what it takes to build the first commercial facility. Washington-based Helion Energy is probably its main American rival, and reckons it could have a plant operating even sooner, by 2028.
In one of my older videos, they said they would have one operational by 2025. And they don't. I had a few different words to say about those guys. Please check it out in the pinned comment down below if you haven't seen that.
They've already built 6 prototypes of their reactor and have signed their own power purchase agreement with Microsoft. Then you've got China. Although it seems to be a bit behind the US on the path to commercial power, the country is running some of the world's largest and most advanced experimental fusion projects.
According to what they say. Look, I know there's first mover advantages with everything, but I would even use ITER as an example. But again, that's a science experiment. In fact, I would argue that ARC is taking a bit of a gamble here, and they're using data from ITER's mission and all the predecessors that have led up to that to leapfrog this technology using better magnets, which could work. It's a risk, but ITER's superconductors, maybe 12 Tesla. These Rebco will take that up to 20, which is promising, but largely untested on large-scale reactor conditions. It could work, but we'll have to see. After all, the neutron environment in fusion is actually more intense because they're at a high energy. Fusion neutrons are about 14 MeV, whereas fission ones average in at about 2. So that's going to correspond to faster structural embrittlement. Not to mention they have more sensitive things like magnets, whereas in fission, it's more of just, okay, will the thing stay in one piece? Things like erosion, embrittlement, and swelling. Fusion, this thing's got to stay magnetic and working and be very magnetic at upwards of tens of Teslas. To give you a sense of scale, an MRI machine's about 3. So these are very strong magnets and very big magnets.
They're planning to raise the bar even further by constructing the first ever fusion fission plant in the next 5 years.
Okay, this isn't as exotic as you might think. It's been around since the 1950s. It's essentially using fusion as a neutron source to drive fission in fertile material. Remember when I said the fusion neutrons are a lot harsher at about 14 MeV? So you can drive fission, even fast fission, in stuff like uranium-238 and thorium-232. And depending on their design, you can have it as kind of a modified spectrum of causing fast fission or absorption, conversion, and thermal fission, kind of like how a breeder reactor works, where thorium-232 absorbs a neutron, goes a couple of beta decays, and you fission the uranium-233. But that is still messy, and you're going to have the same nuclear waste challenges that you would have with any fission reactor.
That's where neutrons made from fusion can cause fission to occur in surrounding materials.
Now, don't worry, we're not going to go into any more detail on that because we think you've had enough science.
Oh, I just did.
For one day. We also don't actually know anything more about it. But the point is, Commonwealth Fusion Systems might be the one to bet on right now, but it's also got quite a bit of competition, and as we've seen before, getting this process right can be extremely difficult.
CFS has been set up with the sole purpose of go build fusion power plants. So I think we are structured to be fast, to be efficient, to be have this very clear mission. Known physics.
That is quite ambitious, and you know what? I wish them all the success in the world, because that is risky from a business standpoint, not from this might cause a crazy accident standpoint. It's not. It's more like if it doesn't work, it just doesn't work, and you just wasted billions of dollars, and you have to deal with unhappy investors.
This new magnet technology, and then a purpose-built organization allow us to move quickly.
By purpose-built, he's meaning strictly for power production as opposed to a large experimental facility designed to do a whole bunch of different things. Purpose-built sounds sexy from an engineering perspective, but at the same time, if it doesn't work, you just put all your eggs in one basket.
Whoever emerges victorious, it's a breakthrough that can't come soon enough. Our planet is set to see unprecedented growth in demand for electricity over the coming years. Rising populations will lead to more housing, business.
I mean, it's an interesting idea, but
and infrastructure. Then you've got the electrification of transport and the rise of power-hungry tech like AI. Wherever it comes from, having a new source of clean, abundant energy can only be seen as a positive. A technology that's promised so much.
Yeah, if this does work, we're still going to need nuclear fission, by the way.
So long. Could finally be unleashed.
Don't forget,
nuclear fission also produces some tritium as a waste product, another way they can work together. I'm curious to see how this goes, but I'm not going to hold my breath. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.